Welcome to another lesson of the course Curves in Engineering and Architecture. We are in the second part of the course, namely Curves in Road Safety. In Module 6, we would like to learn more about transition curves and other relevant issues in road safety. Lesson 6.2 is about vertical alignments in geometric design of roads. Remember that in Module 4 we focused on horizontal alignments that result in comfortable and safe roads. We looked for transition curves with a smooth variation of tangent direction, and we found the clothoid or coniue spiral as a good curve because its curvature is proportional to the arc length traveled. Later, in Module 5 and in Lesson 6.1, we have found a procedure to lay out a clothoid in the field thanks to the parametric equations of the curve. We were able to get these parametric equations in terms of arc length traveled along the curve using mathematical tools as derivation, integration, and polynomial approximation. Now, in Lesson 6.2, we want to find the best shape for vertical alignments. A vertical alignment consists of a series of straight lines and curves giving a profile in the vertical plane. The slope or grade of a line is defined as the tangent of the angle of the line to the horizontal, that is, the vertical displacement over the horizontal displacement. In transportation, grade is usually expressed as a percentage that is equal to 100 times tangent of alpha. For example, a 10% grade means that for every 100 unit of change in horizontal displacement, the elevation changes in 10 units. The length of a vertical curve is measured along horizontal alignment. A point on the curve is specified by its station location on the horizontal alignment and by its elevation. When going up or down, we would like a profile such that the rate of change of grade will be constant. Remember in Lesson 5.1 that sounds to the derivative of the grade with respect to displacement being constant. As the grade or slope of the graph of a function f of x is the derivative of the function f prime of x, then the profile must be the graph of a function whose second derivative is constant. Remember in Lesson 5.2, we can write this information about the second derivative of a function as a differential equation, that is, second derivative of x with respect to x is equal to a constant r, where x is the horizontal displacement and r is the constant rate of change of grade. But we learn how to solve this differential equation. Recalling Lesson 5.2, by integration, that is the opposite process to derivation, f prime of x must be equal to r times x plus a constant g1 that tell us the grade just prior to the curve. Now, by integration again, f of x must be equal to r times half x squared plus g1 times x plus a constant y0 that gives us the elevation of the beginning of the vertical curve at the point BVC. In this way, for vertical alignment, using mathematical tools as derivation and integration of functions, one gets a parabola as the best shape for vertical curves. Moreover, the grade of the tangent to the vertical curve can be expressed as a linear function of the horizontal displacement. Design standards for vertical alignments establish the minimum length of a vertical curve based on side distance, on comfort standards involving vertical acceleration, or on appearance criteria, and also maximum and minimum grade based on the type of road. You can learn more about this at this internet site. Finally, to combine horizontal and vertical alignments, we would like to learn more about drawing curves and tangents in Lesson 6.3.